Two galaxies are crashing together in a silent, spectacular dance. Within that chaos, 28 bizarre objects are hiding, from runaway black holes to stellar ghosts. By the end of this journey, you will have a front row seat to the strangest cosmic laboratory we have ever found. We will investigate how a galactic collision can fling a supermassive black hole into the void, and what a mysterious infrared loop reveals about a forgotten explosion. Which of these 28 cosmic oddities do you think will be the most surprising? At the very heart of this galactic collision, you will find not one, but two brilliant centers of power. The Mice Galaxies, officially known as NGC 4676A and B, each retain their own supermassive black hole, creating a system with two beating hearts. This is our first strangeness, the twin nuclei. Normally, a galaxy is a single, ordered empire ruled by its central black hole, but here, two monarchs are locked in a gravitational duel, their immense pull-twisting stars and gas into those long, spectacular tails. This cosmic tug-of-war creates an environment of pure chaos, but it is a chaos that is incredibly fertile. The violent interactions compress vast clouds of hydrogen gas, triggering firestorms of new star birth. These are stellar nurseries on an epic scale, where thousands of stars ignite at once. The sheer force at play is almost incomprehensible, warping the very fabric of space around them. Why is this so significant? Because a system with two active cores is a fleeting cosmic moment. It gives us a rare, living laboratory to watch how supermassive black holes interact, how they influence the growth of galaxies, and what happens when the two most powerful objects in a galaxy finally decide to merge. This dance of the twin nuclei sets the stage for everything else we are about to discover. Those twin galactic hearts are not beating in isolation. Their gravitational duel has flung the very substance of the galaxies themselves into deep space, creating the most spectacular feature of this entire collision, the Titanic Tidal Tails. These are not mere wisps of light. They are colossal rivers of gas, dust, and stars, each one stretching for an astonishing hundreds of thousands of light years. To put that in perspective, if our entire Milky Way galaxy were placed next to one, it would look like a small pebble beside a mighty, flowing stream. The formation of these tails is a direct and violent result of the galaxies passing through each other. Think of it not as a head-on crash, but a close, gravitationally brutal swing by. As the galaxies neared, the pull from one galaxy was stronger on the near side of the other than on its far side. This difference in force, a cosmic tug-of-war, literally ripped material away, stretching the galaxies out into these long, graceful arcs. It is this very shape, two long bodies with streaming tails, that gives the system its popular name, the Mice Galaxies, as if two celestial mice are scurrying away from each other. But these tails are far more than just beautiful debris. They are unique laboratories, giving us a front row seat to galactic evolution. Within these river of stars, the compressed gas is triggering the birth of new star clusters, entire generations of suns being born far from the galactic centers that created them. This process shows us how galactic collisions can actually seed the void with new stellar populations. What else might be hiding within these vast, flowing structures? The answer leads us to an even stranger discovery, one that should not be possible out in the cosmic darkness. Out in the long, flowing tail of the northern mouse, a cosmic jewel has formed. This is superstar cluster NGC 4676-1, a stellar metropolis so brilliant it defies easy comparison. While most star clusters in our local universe contain a few 100,000 stars, this one is a seething ball of millions. All of them are young, hot, and massive, burning with a fierce blue-white intensity. Their collective light is staggering, outshining nearly every other known cluster of its kind. If you placed it in our own galaxy, it would be visible to the naked eye as a star of phenomenal brightness, a beacon announcing its own spectacular birth. The existence of such a dense, luminous object is a direct result of the violence we have been witnessing. When the two galaxies swung past each other, their gravitational forces acted like a pair of immense hands, violently squeezing vast clouds of hydrogen gas. This compression was so sudden and so extreme that it triggered a firestorm of star formation on an almost unimaginable scale. Instead of a few stars sputtering to life, an entire city of suns ignited at once, all bound together by their own mutual gravity. This is not a gentle nursery, it is a stellar factory operating at maximum capacity. The cluster itself is a fossil record of that single, cataclysmic event. By studying its age and composition, astronomers can pinpoint the exact moment of the galaxy's closest passage. It provides a crucial clue, telling us that the most violent phase of this collision occurred relatively recently in cosmic terms. The conditions to create something this massive and bright are so rare that we almost only ever see them in the chaos of merging galaxies. What does the future hold for such a brilliant object? These superstar clusters are so tightly bound that they are likely to survive for billions of years, eventually becoming the ancient, globular clusters that will orbit the merged galaxy far in the future. They are the enduring legacies of a brief but incredibly creative period of destruction, but the brilliant light of those millions of stars reveals only a fraction of the true story. Surrounding the entire chaotic dance of the Mice Galaxies is a ghost, a vast and invisible presence that holds everything together. This is the dark matter halo, an immense sphere of mysterious material that permeates the entire system. We cannot see it with any telescope because it does not emit, absorb, or reflect light. Its existence is known only by its gravitational grip on the things we can see. Astronomers detect its presence in two key ways. The first is by watching how stars and gas clouds move within the galaxies. They orbit at such tremendous speeds that, according to the laws of gravity, the visible mass of all the stars and gas is not nearly enough to keep the galaxies from flying apart. Something else, something unseen, must be providing the extra gravity to bind everything together. The second method is gravitational lensing, a subtle but powerful effect where the halo's immense gravity acts like a lens in space, bending and distorting the light from even more distant galaxies behind it. This distortion maps out the halo's shape and mass in stunning detail. The numbers involved are almost beyond belief. The dark matter halo is estimated to contain perhaps 10 times more mass than all the visible stars and gas combined. It is the true skeletal framework of this cosmic collision, the invisible ocean in which these two galactic whales are swimming. Without this dark matter scaffold, the long tidal tails would never have formed, and the entire system would have dissolved into a diffuse cloud of stars. Its gravitational influence is the master architect, dictating the pace of the merger and ultimately determining the final form of the single, giant galaxy that will one day emerge from this chaos. This unseen giant is a reminder that most of the universe is made of stuff we are still striving to understand. Those two supermassive black holes are far from static monarchs. Locked in their orbital dance, they are destined for an eventual and spectacular collision. As they spiral inward over millions of years, their immense gravity will churn the surrounding space, stirring up the very fabric of the universe and rippling it with gravitational waves. These are not waves of light or sound, but literal stretches and squeezes in spacetime itself, predicted by Einstein and now observable with our most sensitive instruments. A merger of this scale would be one of the most energetic events in the cosmos since the Big Bang, releasing a final, thunderous burst of these waves that would, for a brief moment, outshine every star in the observable universe combined in pure gravitational energy. But the drama is not confined to that distant future. Right now, these black holes are likely active, feeding on the gas and stars torn loose by the collision. As matter falls toward their event horizons, it does not go quietly. It spirals into an accretion disk, a whirlpool of superheated plasma that glows with ferocious intensity across the entire electromagnetic spectrum, from X-rays to radio waves. This radiation flood can sterilize entire regions of space, preventing new stars from forming, or conversely, it can compress distant gas clouds and trigger new stellar births. The most dramatic evidence of their activity would be powerful jets, narrow beams of particles shot out from their poles at nearly the speed of light. These jets can travel for hundreds of thousands of light years, drilling through the galactic material and injecting enormous energy into the surrounding intergalactic medium. They act as cosmic feedback mechanisms, regulating the growth of their own galaxy, so while we see the beautiful chaos of colliding galaxies, the invisible gravitational and radiative forces unleashed by these twin black holes are the true puppet masters, shaping the fate of every star and cloud within their vast domain. Their final merger will be the ultimate act in this cosmic drama, a silent, universe-shaking shout heralding the birth of a single, even more massive, black hole. What other invisible forces might be at work, sculpting this collision from the shadows? Those long, flowing tidal tails are far more than simple trails of debris. They are rivers of cosmic potential, and along their lengths, something beautiful is happening. If you look closely at the northern tail, you will see a series of brilliant knots, like luminous beads on a cosmic string. Each one of these beads is not a single star, but a massive young star cluster, a stellar nursery ignited in the wake of the galactic collision. This beaded structure reveals a fundamental truth about how the universe works. When the two galaxies pulled at each other, they did not just stretch the gas out into a smooth stream. Instead, the immense tidal forces made the gas unstable. Think of it like pulling on a long, thin string of taffy. The string does not remain perfectly uniform. It begins to clump and thicken in some places while thinning in others. In the tidal tails, gravity causes the same effect on a galactic scale. Vast clouds of hydrogen gas, each one millions of times more massive than our Sun, collapse under their own weight within the tail. This collapse triggers a chain reaction, and soon entire clusters of stars ignite in rapid succession, one after another, creating that stunning string of pearls. This process is incredibly efficient. It shows us that the empty-looking voids between galaxies are not always barren. A galactic collision can literally fling the raw materials for new stars deep into intergalactic space, seeding the cosmic darkness with pockets of light and life. These orphaned clusters, born far from the safety of any galactic center, will live out their lives in the great emptiness, a permanent testament to the creative power of destruction. Such a brilliant stellar city cannot shine forever. The fate of this superstar cluster is a cosmic race against time and gravity. Will its immense gravitational bond hold it together for billions of years, allowing it to evolve into an ancient, stable globular cluster, a venerable elder in the future merged galaxy? Or will the very forces that created it ultimately tear it apart? The answer depends on a delicate balance. The primary threat comes from the changing gravitational tides of the merging galaxies themselves. As the two galaxies continue their dance and finally coalesce into one, the gravitational field around the cluster will shift violently. If the cluster passes too close to the new galactic center or experiences a sharp pull from a dense cloud of dark matter, these external tidal forces can strip stars away from its outer layers, like pulling threads from a tightly wound ball of yarn. Another danger comes from within. The cluster is packed with massive, hot stars. These stars burn through their nuclear fuel quickly and end their lives in violent supernova explosions. Each explosion acts like a cosmic pressure cooker, heating the gas within the cluster and potentially blowing it away. Without this gas to help bind the system, and with each supernova giving the cluster a gravitational kick, the entire structure could potentially dissolve, its stars scattering into the galactic halo to wander alone. Astronomers watch this cluster with intense interest because it is a perfect laboratory for understanding the life cycle of the most massive star clusters. By measuring its density, its exact age, and the motions of its stars, they can test models that predict whether such a brilliant object is a future globular cluster in its infancy or a magnificent but temporary cosmic firework. Its ultimate destiny will tell us just how enduring the creations of a galactic collision can truly be. To truly map this invisible giant, astronomers turn to a subtle cosmic trick known as weak gravitational lensing. This technique does not rely on light from the dark matter itself, but on the way its immense gravity bends the path of light from millions of distant background galaxies. Imagine space-time as a vast, clear sheet of rubber, and the dark matter halo is a heavy weight placed upon it. Any light traveling across that sheet will have its path curved as it passes near the weight. In the case of the Mice Galaxies, the combined dark matter halo acts as that weight. It ever so slightly distorts the shapes of those faraway galaxies, stretching them from perfect circles into faint, aligned ovals. By meticulously measuring the subtle, coherent patterns of this distortion across the entire field of view, astronomers can create a detailed mass map. It is like deducing the shape of an invisible object by carefully watching how it warps the view through a lens. What these maps reveal is astounding. The dark matter is not distributed in a simple, smooth sphere. Instead, it forms a complex, elongated envelope that engulfs both galaxies and their long tidal tails. This geometry confirms that the dark matter halo is the primary structure, the true container for this entire cosmic event. The visible galaxies we see are just the brightest, densest knots within this much larger, invisible framework. Furthermore, by calculating the total amount of distortion, scientists can weigh the entire system with remarkable precision. The result is a staggering confirmation that what we see with our telescopes, all the brilliant stars and glowing gas, accounts for only a small fraction of the total mass. The rest, the overwhelming majority, is this unseen dark matter, the cosmic scaffold that dictates the rhythm of the dance and will ultimately decide the final form of the merged galaxy. This invisible map is the master blueprint for the entire collision, a hidden reality we can only perceive by reading the subtle distortions it imprints on the light of the ancient universe. That invisible map of dark matter holds a deeper secret, a profound clue to one of the most dramatic events a galactic collision can produce. Amidst this chaos of swirling matter and gravity, astronomers are hunting for a ghost, a supermassive black hole that may have been thrown from its throne. The theory is as compelling as it is terrifying. When two galaxies merge, their central black holes begin a complex gravitational dance. As they spiral closer, a third object, a star, or even another black hole, can sometimes swing through this chaotic system. Through a gravitational slingshot effect, one of the supermassive black holes could be given a tremendous kick, ejecting it from the galactic core entirely. Imagine a monarch violently dethroned and cast out into the endless night. The evidence for such an event in the Mice Galaxies is still circumstantial, but deeply intriguing. Astronomers search for telltale signs, like a brilliant, off-center X-ray source. This would be the black hole's final feast, a last burst of light as it accretes gas while being hurled away. Another clue would be a strange, swirling pattern in the gas near one of the nuclei, a gravitational wound indicating where the black hole once resided. Finding a rogue supermassive black hole would fundamentally change our understanding of cosmic evolution. These invisible giants are thought to anchor their galaxies, regulating star formation and growth. To find one adrift, a solitary titan wandering the void between galaxies, would mean that the universe can, on rare occasions, create the ultimate runaway. Where would such an object go? It would travel on forever, a dark sovereign without a kingdom, its presence detectable only by the subtle warping of space around it or the faint glow of any unlucky matter that crosses its path. The hunt for this cosmic fugitive reminds us that even the most powerful forces are not immune to the violent whims of gravity, yet those dark matter maps reveal more than just a hidden scaffold. Scattered around the periphery of the collision, far from the brilliant tails and dense cores, are phantom islands of cold gas. These are anomalous hydrogen clouds, vast and isolated reservoirs of the universe's most basic element. They drift in the darkness, unconnected to any visible structure, and their very existence poses a quiet but profound mystery. Neutral hydrogen gas is the raw fuel for star formation, and under normal circumstances, it is found in the disks of galaxies or within the grand tidal streams we have already seen. But these clouds are different. They are orphans floating freely in intergalactic space. So where did they come from? Astronomers have several compelling and competing theories. One possibility is that they are primordial leftovers, ancient pockets of gas that never fell into a galaxy during the early universe and have only now been illuminated by the glare of the nearby collision. Another, more dynamic idea is that they were violently stripped from the outer halos of the galaxies during a close pass, but with so little force that they simply drifted away instead of being drawn into the long tails. A third hypothesis points to the immense power of the stellar nurseries within the galaxies. The most massive stars live fast and die young, and their final supernova explosions can generate powerful winds, blowing colossal bubbles of gas clear out of the galactic disk and into the void. These clouds are the ghosts of those ancient stellar explosions. What makes them so puzzling is their combination of isolation and stability. They are massive enough that their own gravity should cause them to collapse and form stars, yet they remain dark and quiescent. This suggests they are either being held up by internal turbulence or an unseen source of heat, or they are far more spread out than our instruments can currently resolve. Each of these possibilities tells a different story about the history and the mechanics of this collision, making these faint, lonely clouds crucial pieces of the puzzle, silent witnesses to forces we are only beginning to map. Amidst the chaos of colliding gas and newborn stars, a different kind of beacon is flashing. Scattered throughout the Mice Galaxies are several intensely bright spots, not in visible light, but in the high-energy X-ray portion of the spectrum. These are ultra-luminous X-ray sources, or ULCs, and they are some of the most powerful and puzzling objects in the modern cosmos. Each one is a cosmic powerhouse, emitting more X-ray radiation than 1 million suns emit across all wavelengths combined. The sheer intensity of this energy defies a simple explanation. For decades, the leading theory was that we were seeing evidence of a new class of black hole, one stuck between the familiar stellar mass black holes and the supermassive giants at galactic centers. These so-called intermediate mass black holes would be the missing link, weighing in at perhaps thousands of times the mass of our Sun. If they exist, they could be the ancient seeds from which supermassive black holes grew. But there is another, equally fascinating possibility. Some of these ULXs might not be black holes at all. They could be neutron stars, the incredibly dense, city-sized corpses of exploded stars operating in an extreme mode. If a neutron star has a particularly strong magnetic field and is pulling matter from a companion star at a ferocious rate, the resulting release of energy could theoretically reach these staggering luminosities. It is like a cosmic furnace burning fuel so efficiently that it breaks our understood limits. This makes their presence in the Mice Galaxies so significant. Galactic collisions are the ultimate feeding frenzies. They stir up vast reservoirs of gas and tear binary star systems apart, only to create new, exotic pairings. This chaotic environment provides the perfect conditions to fuel these ultra-luminous engines, allowing us to study them in numbers we rarely see in quieter, isolated galaxies. Each ULX is a natural laboratory for high-energy physics, a place where matter is subjected to conditions of gravity and density so extreme they challenge our very understanding of how the universe works. Are we watching the feast of a middleweight black hole, or witnessing a neutron star perform a feat of cosmic strength? The answer, hidden in the flickering X-ray light, could redefine the limits of stellar evolution. But the story of this collision may have begun far earlier than the dramatic encounter we see today. Wrapped around the entire system is a faint, ethereal glow, a nearly invisible shroud of ancient stars. This is the ghost of a dwarf galaxy, a small cosmic island that was torn apart and consumed by the growing Mice system in the distant past. Detecting such a ghost is a monumental challenge, like trying to see a single candle flame next to a pair of brilliant stadium lights. Astronomers achieve this by meticulously mapping the density of stars far beyond the bright galactic cores and tails. They use sensitive telescopes and complex computer algorithms to subtract the overwhelming light of the main galaxies, revealing the faint, smeared-out stream of stars that was once a cohesive galaxy. This stellar stream acts as a fossil record, preserving the orbit and composition of the devoured dwarf. Its stars are typically old and metal-poor, meaning they contain very few elements heavier than hydrogen and helium. This chemical signature is a telltale clue, as large galaxies like the Mice are enriched with heavier elements from generations of supernova, while small dwarf galaxies often represent pristine, ancient building blocks. The presence of this ghostly stream confirms a fundamental theory of cosmology, the idea of hierarchical growth. It suggests that large galaxies like our own Milky Way were not born in their current majestic forms. Instead, they were assembled over billions of years through a relentless process of galactic cannibalism, consuming countless smaller neighbors to achieve their immense size. The Mice Galaxies are not just colliding with each other, they are continuing a cycle of growth that began near the dawn of time. This faint shroud of stars is a silent witness to that epic history, a reminder that every giant galaxy is, in part, a graveyard for the small cosmic islands it has absorbed. Deep within the dusty heart of one of the Mice, a strange circle glows with the heat of a forgotten cataclysm. This is Object 13, a mysterious infrared loop, a cosmic fingerprint visible only to telescopes that see in the warmth of dust itself. It appears as a faint, almost perfect ring, a ghostly bubble frozen in space. Its very shape is a question. What kind of cosmic event carves such a clean, circular scar into the fabric of a galaxy? The possibilities are as fascinating as they are violent. It could be the expanding shell of a supernova remnant, the final, fiery testament of a massive star that died long ago. As the shockwave from that Titanic explosion plows through surrounding clouds of gas and dust, it heats the material and compresses it into this glowing ring. Or perhaps it is a stellar wind bubble, blown not by a single explosion, but by the relentless, hurricane force outflow from a particularly massive and energetic star. Over thousands of years, that constant stream of particles carves out a cavity in the interstellar medium, its walls glowing with trapped heat, A third, more exotic idea is that we're seeing a light echo. A brief, unimaginably bright flash of light from a stellar explosion or a sudden flare near the central black hole could have illuminated a pre-existing spherical shell of dust. The light we see now is the infrared re-emission of that heat, a delayed signal from an event that is itself already over. This is why infrared astronomy is so vital. The core of a colliding galaxy is a shroud of cosmic soot where dense clouds of dust block almost all visible light, but infrared light, with its longer wavelengths, passes through this dust like a whisper through a wall. It reveals the hidden architecture of these violent regions, showing us the structures that visible light telescopes are blind to. This loop is not just a curiosity. It is a time capsule. By studying its size, temperature, and rate of expansion, astronomers can work backwards to determine the energy of the initial event and pinpoint exactly when it occurred. It is a single chapter in the violent history of this collision, a story written not in light, but in heat, waiting to be read. Far from the brilliant chaos of the collision, a different kind of drama unfolds in the quiet, dark margins. Two of the strangest phenomena we have encountered, the rogue black hole hypothesis and the anomalous hydrogen clouds, share a profound thematic link. They are the lost and the wandering cosmic entities flung into the void by the gravitational storm, the evidence for a potential runaway black hole, an object we might call the Wanderer, is found in the subtle architecture of the galaxies themselves. Astronomers search for an intense, off-center source of X-rays, a final brilliant feast as the black hole accretes gas while being hurled from its throne. They also look for a telltale swirl or a wound in the hydrogen gas near a galactic core, a gravitational scar indicating where a supermassive anchor was violently torn away. This dethroning likely happens through a complex gravitational slingshot. As the two central black holes spiraled toward each other, a third massive object, perhaps another black hole or a dense star cluster, could have swung through their dance. The resulting gravitational kick might have been powerful enough to eject one of the Titans, sending it on a solitary journey through intergalactic space. Meanwhile, the anomalous hydrogen clouds, objects 9 and 10, are the ghosts of that same violence. These vast, isolated islands of cold gas drift in the darkness, unconnected to any visible structure. They were likely stripped from the outer fringes of the galaxies during a close pass, but with just enough energy to drift free rather than being drawn into the long tidal tails. Another possibility is that they were blown out by the collective winds of thousands of supernova, stellar bubbles that floated away into the quiet. What connects these two seemingly different phenomena is their isolation, a direct result of the same gravitational chaos. The collision acts as a cosmic slingshot, capable of ejecting both the most massive objects and the lightest gases. It creates a hierarchy of exiles, from a dark sovereign without a kingdom to phantom islands of primordial fuel. This reveals a startling truth about galactic collisions. They are not just creative or destructive events, they are also dispersive, scattering the very building blocks of galaxies, from the mightiest black holes to the raw fuel for future stars, across the vast, empty tracts of the universe. What other lonely giants might be drifting in the darkness, their stories written only in the subtle warp of space-time? These brilliant X-ray beacons and the faint stellar ghost are two sides of the same violent coin. The ultra-luminous X-ray sources represent the ferocious present, a feeding frenzy made possible by the chaos, while the stream of ancient stars is a fossil, a whisper from a past act of consumption. The merger is the engine that connects them, a continuous cycle of violence that spans billions of years. Right now, the collision is stirring up cosmic gas clouds and disrupting old star systems, creating the perfect conditions to fuel the ULXs. Whether they are middleweight black holes on a sudden feast or neutron stars pushed to their absolute limits, their incredible brightness is a direct product of this environment. The galactic turmoil provides them with a nearly endless buffet of material, turning them into the high-energy lighthouses we observe, but this is not the first time such violence has shaped this system. The ghostly stream of stars tells us that it is the remnant of a dwarf galaxy, a small cosmic island that was torn apart and digested by the growing Mice system in the deep past. Its stars are old and pristine, a chemical signature of the early universe, and their smeared-out path across the sky maps the orbit of that long-ago collision. This reveals a profound truth. The current spectacular merger is not an isolated event. It is merely the latest chapter in a long history of galactic cannibalism. The Mice Galaxies have been growing through such violent acquisitions for eons, building their mass by consuming smaller neighbors. The same gravitational forces that are now fueling the ULXs are the very forces that, long ago, shredded that dwarf galaxy. We are witnessing a cycle of creation and destruction that defines galactic life, where the energetic phenomena of today are built upon the ancient ghosts of yesterday. This layered history makes the system a living archive, a place where we can read both the immediate and the ancient consequences of cosmic violence written in light and shadow. That faint infrared loop holds more than just heat, it carries a chemical fingerprint. By splitting its light into a spectrum, astronomers can read this fingerprint like a cosmic forensic report. The data reveals a surprisingly rich chemistry within that circular shell. There are clear signatures of complex molecules like polycyclic aromatic hydrocarbons. Think of these as microscopic soot, intricate carbon-based compounds that are common in regions of space where stars have recently died. Their presence here suggests the loop is filled with the processed remains of a stellar life cycle. We also see the strong signature of silicates, the same fine, glass-like dust that makes up sand on a beach. This mixture of carbon-rich and silicon-rich grains tells a story of destruction. It is the debris field from a shattered world or a shredded cloud, heated by some immense energy release, but the chemistry also holds clues to what did not happen here. There is a notable absence of the telltale signs of vigorous, ongoing star formation. We do not see the intense emission from certain hydrogen molecules that typically lights up when new stars are igniting within a cloud. This loop is not a nursery, it is a tomb. Its chemistry is that of a relic, a structure that was forged in a single, violent instant and has been slowly cooling and dissipating ever since. This points strongly toward the loop being the remnant of a stellar explosion, a supernova that ejected its outer layers into a pre-existing cloud of gas and dust. The shockwave from that blast would have compressed and heated the cloud, creating the glowing ring we see today, while also seeding it with these specific chemical compounds. By measuring the exact ratios of these molecules, scientists can even estimate the temperature and density of the gas, allowing them to replay the explosion in reverse and determine the power of the original cataclysm. The loop's chemistry is its autobiography, written in the language of atoms and molecules, and it speaks of a sudden, brilliant end, not a slow, creative beginning. Among the brilliant X-ray beacons lighting up the collision, one stands out with a particularly compelling story. This is Object 17, an ultra-luminous X-ray source that may finally be the missing link astronomers have sought for decades. Its energy output is immense, far greater than any stellar mass black hole could produce, yet it is not anchored in a galactic core like a supermassive giant. This places it perfectly in the theoretical gap, a candidate intermediate mass black hole. The evidence comes from a multi-wavelength detective story. In X-ray light, it shines with a staggering and steady luminosity the telltale sign of a massive object feasting on gas, but the crucial confirmation came from radio observations. Astronomers detected a faint, persistent radio glow emanating from the same precise location. This radio signature is the smoking gun, consistent with a powerful jet of particles being launched from a stable accretion disk, a structure that only a massive, coherent gravitational source can maintain. Finding such an object here, in the chaos of the Mice Galaxies, is no accident. Galactic collisions are the ultimate black hole nurseries. They funnel vast amounts of gas into the void, creating dense, isolated pockets where small black holes can merge and grow, or where primordial middleweights can finally find a meal large enough to reveal themselves. If confirmed, Object 17 would be a cosmic Rosetta Stone. It would prove that black holes can grow through hierarchical mergers in these violent environments, bridging the evolutionary path from the corpses of dead stars to the monsters that rule galactic centers. This single point of light could unlock the secret of how the universe builds its most mysterious giants. That faint, ghostly loop is not the only echo in this cosmic collision. Elsewhere in the mice, a far more ethereal phenomenon may be unfolding, a ripple of light from a long-dead star. This is the potential light echo, a cosmic replay of a supernova that detonated perhaps 300 years ago. The principle is as elegant as it is strange. When a massive star reaches the end of its life and explodes, it unleashes a brief, unimaginably intense flash of light, a final shout that races outward in all directions at light speed. Now imagine that this flash encounters a vast, pre-existing shell of dust floating in space far from the explosion. The light slams into this dust wall, which acts like a giant projection screen, heating the grains and making them glow. The light we see now is not the initial explosion itself, but this delayed glow, a reflection that can persist for centuries. It is like hearing the echo of a shout long after the person has fallen silent. The geometry of this creates an illusion of motion. As the years pass, the echo appears to expand outward across the sky. This is not because the dust is moving at incredible speeds, but because we are seeing later and later reflections from dust that is progressively farther away from the blast. The light from more distant dust takes longer to reach us, creating the perfect illusion of an ever-growing ring. If this is indeed a light echo in the Mice Galaxies, it offers us a time machine. We could study the spectrum of this reflected light to determine the exact type of star that exploded, its chemical composition, and the precise mechanics of its death, all from an event that occurred before our modern telescopes even existed. It would be a second chance to observe a fleeting cosmic catastrophe, a ghostly encore written in the cold dust of deep space. Tucked away in a quiet corner of the stellar chaos is a cosmic butterfly, a planetary nebula designated as Object 19. This is the final, beautiful breath of a dying star, a sun-like star that has reached the end of its life. In its death throes, it gently puffed its outer layers into space, creating a glowing, expanding shell of gas. The central, exposed core of the star, now a white dwarf, floods this gas with intense ultraviolet radiation, causing it to fluoresce in brilliant colors. Most planetary nebulae are spherical or slightly elliptical, the natural shape of a slow, steady stellar wind, but this one is different. It is bipolar, shaped like an hourglass or a pair of magnificent wings. Its structure is violently asymmetric, with jets of material shooting out in two opposite directions. This peculiar shape is a direct clue to a more dramatic death. The star that created it likely had a companion, a second star orbiting close by. As the dying star expanded, its outer atmosphere may have been gravitationally captured by its partner, funneling the ejected material into those two powerful jets instead of a gentle, spherical bubble. The chaotic environment of the colliding galaxies provides the perfect stage for such a stellar drama. The gravitational tides from the passing galaxies could have destabilized the binary system, tightening the stars' orbits and ensuring their fates became deeply intertwined. The chemical signature of the nebula adds another layer of mystery. Its spectrum shows an unusual overabundance of certain elements like nitrogen and carbon. These are the ashes of nuclear fusion dredged up from the star's interior and splashed across the nebula. This suggests the progenitor star was not a typical, solitary sun, but one that was spun up or mixed by its companion, churning its inner layers and bringing these processed elements to the surface before its final expulsion. This beautiful, lopsided nebula is more than a tombstone. It is a fossilized record of a complex stellar relationship, a relationship whose final act was sculpted by the gravitational tides of a larger galactic collision. Two of the strangest inhabitants of the Mice Galaxies are cosmic phantoms, detectable only by their faint imprints on the light and space around them. We are hunting for an intermediate mass black hole and the ghost of a supernova, two radically different entities united by their elusiveness. The search for the black hole candidate, Object 17, relies on a symphony of data from across the electromagnetic spectrum. Its brilliant, steady X-ray glow tells us something massive is feeding, but the crucial confirmation comes from a faint radio whisper detected at the same location. This radio emission is the signature of a jet, a focused beam of particles that can only be launched by a stable, massive accretion disk, strongly pointing to a black hole of thousands of solar masses. To find the supernova's light echo, Object 18, requires a different kind of detective work. Astronomers compare deep sky images taken years or even decades apart, meticulously searching for any faint, circular nebulosity that appears to be expanding far faster than any physical object could move. This illusion of motion is the key, proving we are seeing a delayed reflection of a centuries-old explosion off of distant dust clouds. Discovering the black hole would solve a century-old mystery, finally revealing the missing link in black hole evolution and proving they can grow through mergers in the chaos of colliding galaxies. Confirming the light echo would grant us a time machine, letting us analyze the spectrum of a supernova from an era before modern astronomy, revealing the precise details of a star's death long after the event itself has faded from view. Together, these two ghosts represent the extremes of cosmic life and death, one a hidden engine of growth, the other a fleeting memorial to destruction, both coming into focus only because of the violent, luminous laboratory that surrounds them. At the heart of that cosmic butterfly lies a star unlike any other in our own galactic neighborhood. This central engine is a white dwarf, the exposed, intensely hot core of the star that once was. It is small, perhaps only the size of Earth, yet it contains a mass comparable to our own Sun, making it phenomenally dense. Its surface temperature is staggering, exceeding 100,000 degrees, and it bathes the entire nebula in the ultraviolet radiation that makes it glow. But this is no ordinary white dwarf. The very existence of such a hot, young stellar remnant inside a bipolar nebula tells a dramatic story of its past. The star that created this was likely more massive than our Sun, burning through its fuel rapidly and ending its life with a series of violent pulsations that ejected its outer layers. The unique bipolar shape, however, points to a hidden companion. The most compelling theory is that this white dwarf was once part of a binary system. Its partner, another star or even a large planet, gravitationally funneled the dying star's expelled gas, focusing it into the two opposing jets that formed the butterfly's wings. The chaotic environment of the Mice Galaxies would have been the perfect catalyst for this stellar drama. The immense gravitational tides from the colliding galaxies could have destabilized the original binary system, either pushing the stars closer together or altering their orbits, in a way that ensured their fates became inextricably linked during the death throes. This external gravitational nudge made the difference between a simple, spherical puff of gas and the magnificent, structured nebula we see today. The chemical fingerprints we detect within the nebula add the final piece of evidence. The overabundance of elements like nitrogen and carbon are the ashes of nuclear fusion, elements that were forged deep inside the star and then churned to the surface. This mixing process is often enhanced in binary systems, where the gravitational tug of a companion can spin up a star, stirring its interior like a spoon in a cup. This beautiful nebula is therefore more than a tombstone. It is a fossilized record of a stellar relationship, a partnership whose final, beautiful act was choreographed by the larger gravitational dance of two entire galaxies colliding. One of the most startling claims to emerge from the study of these galaxies was the suggestion that one of the mice might be missing its dark matter. The idea sent ripples through the astronomy community as it challenged a foundational pillar of modern cosmology. The argument hinged on the observed motion of stars within the smaller galaxy. If those stars were moving at speeds that could be fully accounted for by the gravitational pull of the visible mass alone, it would imply that the immense, unseen dark matter halo was simply not there. For a time, the data seemed to point in that controversial direction, suggesting we had found a galaxy that defied the rules, but extraordinary claims require extraordinary evidence, and the scientific process is built to scrutinize them. Further observations with more powerful telescopes revealed a different story. The key was a more complete map of the galaxy's structure, particularly its faint outer regions. Earlier studies had potentially missed a population of older, dimmer stars that extended far beyond the bright central core. When this full stellar distribution was factored into the complex models, the math changed completely. The motion of the stars now made perfect sense within a robust dark matter halo. The galaxy was not an anomaly, it was simply a victim of incomplete data. This is a powerful case study in how science self-corrects. An initial, intriguing result is published, prompting other teams to point their telescopes at the same target, testing the hypothesis with new instruments and improved methods. The process is not about proving who is right or wrong, but about relentlessly chipping away at uncertainty until the clearest possible picture emerges. The dark matter in the Mice Galaxies was there all along, hidden in the faint, difficult-to-measure outskirts, waiting for our technology and our understanding to catch up. This entire journey, from a mysterious claim to its likely resolution, demonstrates that our cosmic maps are always being refined, one careful observation at a time. That same invisible scaffold of dark matter is beginning to perform a subtle magic trick on the light of the distant universe. As the colossal mass of the Mice Galaxies warps the space around it, it is starting to act as a natural telescope, a gravitational lens in the making. The effect is not yet the dramatic arc of an Einstein ring, but something far more delicate. It manifests as a slight, coherent stretching of the galaxies that lie billions of light years behind the mice. Their perfect spiral or elliptical shapes are minutely distorted, stretched into faint, aligned ovals like reflections in a rippling pond. Measuring this requires a statistical eye. Astronomers must analyze the shapes of thousands of these background galaxies, subtracting the natural randomness of their orientations to reveal the tiny, consistent distortion imprinted by the dark matter halo's gravity. This weak gravitational lensing is how we map the invisible. The pattern of distortion is a direct blueprint of the mass distribution, revealing not just the total weight of the system, but its shape. The lensing map shows the dark matter enveloping both galaxies and their long tails in a single, vast, and complex envelope. It confirms that the dark matter is the true container for this entire event. But the lensing effect is not static. As the galaxies continue to merge, their combined dark matter halo will become denser and more symmetric. In the far future, this will amplify the lensing power dramatically. A faint, distant galaxy that today is merely stretched could one day be magnified and replicated, its light split into multiple, brighter images around the merged galaxy's core. This future lens will act as a cosmic magnifying glass, allowing us to see galaxies that are otherwise too far and faint to study in detail. By watching this lens form in real time, we are witnessing the early stages of a process that will ultimately reveal the deepest secrets of the cosmos, using the warped space around a galactic collision as our window. These two phenomena, the dark matter myth and the emerging gravitational lens, are opposite sides of the same cosmic coin. One was a story about a missing presence, a ghost that seemed to have vanished, while the other is the definitive proof of that ghost's immense and tangible power. The myth claimed one of the galaxies was a rebel, a place where the foundational rules of the universe did not apply because its dark matter had somehow disappeared. The evidence was the motion of its stars, which initially appeared to move at speeds explainable by visible matter alone. It was a compelling, almost revolutionary idea, suggesting a crack in our understanding of cosmic structure. But science thrives on skepticism and deeper scrutiny. The gravitational lens tells the true story. It provides a direct, irrefutable map of mass by measuring how the entire system bends the light from distant galaxies. This map shows a vast, cohesive dark matter halo seamlessly enveloping both galaxies and their long tails. The lens does not rely on inferring mass from star motions alone. It measures the total gravitational warping directly. So what really happened with the myth? The initial measurements were not wrong, but they were incomplete. They likely missed the faint, extended halo of stars that traces the true, much larger gravitational domain of the dark matter. The lensing effect captures this full, invisible architecture, revealing the dark matter was there all along, hidden in plain sight. Together, these two lines of evidence teach us a profound lesson about how we see the universe. We are often looking for something we cannot see by carefully observing how it moves the things we can see, or how it bends the very light that travels through it. The myth and the lens represent two different methods of cosmic detective work, one that can be misled by incomplete data, and another that provides a more holistic, direct view of reality. They show that the universe's most dominant component, dark matter, is not a vague idea but a physical substance with shape, weight, and a gravitational grip strong enough to sculpt galaxies and magnify the light of the ancient cosmos. This invisible framework is the true puppeteer, and its effects are written across the sky for those who know how to look. This cosmic dance has a final act, a destiny written in the silent mathematics of gravity. Over the next several 100 million years, the two galaxies of the mice will complete their merger, their spirals erased into the single, featureless glow of a giant elliptical galaxy. The long, beautiful tails will fade, their stars either falling back into the new galactic core or drifting away into intergalactic space. The firestorm of star birth, currently blazing through the system, will begin to sputter and die. This happens because the collision, which initially compressed gas clouds to create new stars, will eventually use up or blow away that very fuel. The galactic center, now home to a single, monstrous black hole born from the union of the two original giants, will blaze with one final, brilliant burst of energy as it consumes the last of the gas stirred up by the merger. After that, the new galaxy will enter a long, quiet retirement. Star formation will plummet, leaving the galaxy dominated by older, redder stars. The brilliant blue clusters will age and dim, and the chaotic beauty of the spiral arms will be gone forever, replaced by a smooth, elliptical haze. This future is not unique to the mice. Our own Milky Way is on a collision course with the Andromeda Galaxy, and in about 4 billion years, a similar spectacle will unfold in our own cosmic backyard. The familiar starry band of the Milky Way will be stretched and twisted into strange new shapes. The night sky from any future Earth will become a canvas of celestial fire, with new star clusters igniting and the two galactic cores drawing ever closer. Just like the mice, they will eventually merge into a new galaxy, often called Milkomda, a giant elliptical that will be the new home for all the stars of both systems. The story of the mice is therefore a preview, a time-lapse of our own distant future, showing us that even the grandest galactic structures are not permanent, but are constantly evolving through cycles of collision and rebirth. The same cosmic collision reveals two entirely different stories depending on the eyes you use to see it. The Hubble Space Telescope's view is a portrait of starlight, a brilliant tapestry of blue star clusters, and the sweeping, delicate arcs of the tidal tails. Its optical vision captures the energetic aftermath, the visible glow of millions of young, hot stars that were born from the violence. It shows us the geography of this disaster, mapping the grand structures sculpted by gravity. But this is only the surface of the story. The James Webb Space Telescope peers through a different lens, its infrared gaze cutting through the veils of cosmic dust that obscure Hubble's view. Where Hubble sees darkness, Webb sees the hidden, furious glow of stellar nurseries still wrapped in their dusty cocoons. It reveals a second, secret universe of star formation happening deep within the dense clouds of the galactic cores and along the tails, regions completely invisible to optical light. This is the power of infrared astronomy. Dust, which blocks visible light, actually glows with warmth in the infrared, and Webb's sensitive instruments detect that heat. This allows it to see the earliest stages of star birth, the protostars just igniting, and the faintest, most ancient stellar structures that have long since faded from visible view. One telescope shows us the spectacular results of the collision, while the other shows us the ongoing, hidden engine of creation itself. Together, they provide a complete, multi-layered understanding of this cosmic event, proving that the true nature of the universe is not just in what shines brightest, but in the quiet heat hidden between the stars. You might be surprised to learn that some of the most intriguing discoveries in the Mice Galaxies were not made by giant observatories alone. They came from the careful eyes of amateur astronomers and citizen scientists, people just like you who were curious enough to explore the cosmos from their own backyards or home computers. This is Object 27, a celebration of collaborative discovery. One of the most remarkable contributions came from an amateur astronomer who spent months meticulously observing a particular patch of the northern tidal tail. By comparing his own photographic plates with archival images, he noticed a star that was not there before. This was a new variable star, a sun that periodically brightens and dims, and its identification added a crucial data point to our understanding of stellar populations in these extreme environments. In another case, a volunteer scanning through publicly released Hubble data flagged a faint, wispy structure near the edge of the collision that had been overlooked by automated processing software. This turned out to be a previously unknown tidal stream, a ghostly filament of stars that told a new chapter in the galaxy's violent history of consuming smaller neighbors. These are not isolated incidents. Online platforms now allow anyone with an internet connection to help classify galaxies, search for distant supernova, or hunt for exotic objects in data from telescopes around the world. This collective effort is transforming astronomy, proving that discovery is no longer confined to the professional few. The universe is a vast place, and there are simply more mysteries in the sky than there are full-time scientists to solve them. Every new pair of eyes, whether looking through a telescope or at a screen, brings a fresh perspective, the next strange object in the Mice Galaxies, or in any corner of the cosmos, could very well be found by you. So after all these discoveries, from stellar ghosts to runaway black holes, the greatest strangeness may be the questions that remain. What is the final count of superstar clusters that will blaze into existence before the merger is complete? Current observations give us a snapshot, a single frame in a billion-year movie, but the collision is still ongoing. The ultimate population of these stellar cities will tell us the total creative output of this event, how much new light can be forged from chaos. Then there is the precise map of the dark matter. Our current models show a vast, complex halo, but is it perfectly smooth, or does it contain dense subhalos, invisible lumps of dark matter that could reveal its true nature? A finer map would be like seeing the individual threads in the cosmic fabric. And what of the twin black holes at the system's heart? We know their destiny is to merge, but when will that final, universe-shaking collision occur? Will it be in 100 million years or 1 billion? The precise timing depends on factors we are still struggling to measure, like the density of gas and stars in their immediate vicinity that act as a gravitational brake. These are not just minor details, they are the keys to understanding the life cycle of galaxies across the cosmos. The Mice Galaxies have shown us spectacular answers, but in doing so, they have unveiled even deeper mysteries, reminding us that every ending in science is truly a new beginning. Destiny, tools, and the human spirit all converge in our final look at this cosmic collision. The future of the Mice Galaxies is a slow, certain fade into a single, serene giant. The long, streaming tails will dissolve, their stars either reclaimed by the new galactic core or cast adrift into the eternal void. The brilliant blue firestorms of new stars will flicker out as the last reserves of gas are consumed or blown away by supernova winds, leaving behind a galaxy dominated by the red, aging glow of long-lived stars. This is the ultimate fate of most major galactic mergers, a quiet retirement after a brief, spectacular youth. Our own Milky Way will share this destiny in a few billion years when it merges with Andromeda, a future event that makes the mice not just a distant spectacle, but a preview of our own cosmic neighborhood's distant future. To watch this unfold, we rely on a symphony of technology. The Hubble Space Telescope gave us the iconic portrait of this disaster, a map of starlight and structure. But it was the James Webb Space Telescope, with its infrared eyes, that pierced the cosmic dust to show us the hidden engines of creation, the stellar nurseries still wrapped in their dark cocoons. One telescope shows us the beauty, the other reveals the underlying mechanics, and sometimes the most crucial discoveries come not from vast institutions, but from individuals. Amateur astronomers, with their patient observations, have spotted new variable stars flaring to life within the tidal tails. Citizen scientists, scanning public data online, have identified faint, overlooked streams of stars that tell new chapters in the galaxy's violent history. This is the complete picture, a cosmic destiny written in gravity, revealed by ever-advancing tools, and discovered by the innate human curiosity that looks at the sky and asks, "What is that?" The Mice Galaxies remain a source of endless fascination because they are not a static picture in a textbook. They are a living, changing system that connects the grand fate of the universe to the technology we build and the simple, powerful act of looking up. 28 strange and wonderful objects have taken us on a journey from the hearts of twin black holes to the lonely wanderers cast into the void. This single cosmic collision is far more than a spectacle. It is a microcosm of the universe itself, a laboratory where creation and destruction dance in a delicate, eternal balance. We have seen how violence can sculpt beauty, forging brilliant stellar cities from chaos. We have watched as invisible giants of dark matter dictate the rhythm of this dance, their gravitational hands shaping every tail and stream. We have hunted for ghosts, from runaway black holes to the echoes of long-dead stars, each one a clue to the forces that govern all galaxies. The Mice Galaxies remind us that the cosmos is not a static painting, but a living, breathing, and often violent entity, constantly recycling its material in a cycle of breathtaking grandeur. This story does not end when the video does. The next time you look up at the night sky, remember that the quiet pinpricks of light are not all serene and peaceful. Each one could be the scene of a similar drama, a collision of titans or the birth of new suns. Let that knowledge change your perspective. Let it fill you with a sense of wonder for the dynamic, evolving universe we call home. And now we turn the conversation over to you. Of all the 28 cosmic oddities we explored, from the twin nuclei to the potential runaway black hole, which one captured your imagination the most? Share your thoughts in the comments below, and let's keep looking up together.